What are computer graphics? Well, technically, computer graphics are anything which is displayed on a computer screen. But typically, when people use the phrase computer graphics, they are simply referring to images and pictures. So, understanding computer graphics is not essential to learning how to program a website. But, like anything else in life, the more knowledge you have, the better equipped you will be to grasp the nuances of what you are creating. So, before we talk about graphics and images on computer screens, let's review how we got here in the first place. Thousands of years ago, human beings started to create pictures with stone carvings. Then our technology advanced to paintings, followed by the printing press, and finally to photography, the most advanced form of analog image creation ever invented. In the 1920s, we invented the very first electronic images, television. Now, many people mistakenly think television was invented in the 1950s. Now, while it is true that a majority of American homes began to own a television set in the 1950s, the technology was actually invented 30 years earlier. Although the technology has advanced dramatically in the last century, the foundational elements of television remain the same today as they did a century ago. Computers also display electronically generated pictures on some type of monitor or screen. A computer screen can be used on desktops, laptops, a cell phone, tablet, or even a watch. Regardless of the format of the screen, the function is always the same. We are converting visual images into electronic files, which are displayed on the screen as pinpoints of light. So I want you to remember that phrase, pinpoints of light. At some period in your life, I'm sure you've played with a toy like a light bright, or just looked really close at a television or a computer screen, and you could actually see all the individual little lights which create the image. Now, as we move away from those pinpoints, our mind blends those dots together to form a single image, much like a pointillist painting. So, pointillist paintings use tiny dots of paint to create the image. Anyone with a decent art education or a love for Ferris Bueller is familiar with the famous pointillist painting, A Sunday Afternoon on the Island of La Grande Jetée by Georges Seurat. I'm probably pronouncing that wrong. Let's do a voiceover. This is how it's actually pronounced.
Georges Seurat.
Ah, see, there you go. That's the way you say it. So, the smaller those dots of paint are on the canvas, the more detailed the image appears as we move away from it. Computer screens function in a very similar fashion. Instead of tiny dots of paint, they use tiny dots of light. And as we move away from those dots, they blend together to make an image. So, there are two words you need to know which measure the quality and sharpness of that image: pixels and resolution. Pixels are what we call the little dots, the pinpoints of light. Resolution is a measurement of the quantity of those pixels. Obviously, the more pixels we have, the higher the resolution. The higher the resolution, the more crisp and sharp and clear the image appears. Resolution is typically expressed in a term called dots per inch, or DPI, or pixels per inch, PPI. So you follow so far? It's pretty simple, right? The physical screen has pixels and resolution, and the computer file, which generates that image, also has pixels and resolution. A great analogy is to imagine your computer monitor is a window screen, and the image file saved in the computer is a pointillist painting on the other side of the screen, okay? So all the squares in the screen are pixels, and all the dots of paint are also pixels. Now, the screen and the painting are two separate things, but they both have pixels. Now, see, that's why I like using the screen/painting analogy, because it becomes far easier to understand. So the dots of paint and the squares on the screen, they're not related in any way. But the density of that screen combined with the density of the dots of paint could make for a vastly different looking image. Now, my analogy is not 100% accurate because the pixels on the monitor are a virtual thing. When you physically move your eye up close to a monitor, the physical dots you see are tiny diodes which emit light. On average, it takes 3 of those physical diodes to create 1 virtual pixel. Is that confusing? Okay, let's go back to the window metaphor. Imagine you have a window that is 3 feet across and 2 feet high. Now imagine you swap out the screen for screens with different densities. So you are changing the resolution of the screen, but the window always remains 3 feet by 2 feet. So computer monitors are the same. We can alter the virtual resolution of the display even though the physical dimensions of the screen never change. So, if we look at the screen resolution of a monitor, we can see how it can be changed. As we go down to smaller resolutions, objects on the screen obviously look larger because we are using less pixels to generate the image in the same physical space. However, you'll also notice that there are recommended sizes. Now, this is because the monitor is designed to be displayed at an optimal resolution based upon the capabilities of the electronics. Early color computer monitors, starting around the 1990s, typically had a resolution of around 800 by 600 pixels. Those numbers are telling you the quantity of pixels being shown on the monitor, 800 horizontally and 600 vertically. Like standard definition television sets, these are also known as 4:3 monitors because the proportion of the dimensions, known as an aspect ratio, was 4 units across to 3 units high. Now, the most common resolution on most monitors in the year 2020 is 1920 by 1080, also called high definition, or HD monitors. Now, once again, these have 1,920 horizontal pixels and 1,080 vertical pixels. They are also known as 16 by 9 monitors because the aspect ratio is 16 units across to 19 units high. Or wait, I said that backwards. it's 16 across to 9 high, right? So 4K monitors, they have quadruple the resolution of HD, or 3840 by 2196 pixels. All starting to make sense? So when you think of monitor resolutions and their pixels, like the dots of a pointillist painting, you start to comprehend why 1920 by 1080 HD screens are clearer than 800 by 600 monitors, and why 4K images are sharper than HD. So, now that you understand what pixels and resolution are, let's look at the final topic, one which always confuses people, and that is scaling. Altering the size and scale of images is where people start to get lost when it comes to computer graphics. Here is an example. This is an actual quote I recently had from a client, and 60% of the sentences are totally wrong. The ones in green are true, the others are totally false. The pixels are defining the length and width. The DPI defines the clarity of the image. Typically, digital is 72 DPI. However, DPI can also make the file size smaller or larger. For icons like this, they can typically have a lower DPI to make the file size in kilobytes the right size for the software. Okay, DPI does not define the clarity of the image. DPI is simply a measure of the number of pixels available. DPI does not make a file size smaller or larger. Again, DPI is simply a measure of the number of pixels available. And that last sentence, for icons like this, they can typically have a lower DPI to make the file size in kilobytes the right size for the software. I can't even comment on that because it makes no sense. They think the file size of an icon has to fall in a certain range for certain software? There's no such thing. This was written by an alleged graphic designer, someone who should be an expert in this topic. But even graphic designers can be very poorly educated when it comes to understanding how graphics actually work. Let's get back to scaling. As you blow images up to larger sizes or shrink them down to smaller sizes, people never really grasp what is happening. And because we're usually talking about virtual sizes in some electronic format, it's understandable for people to be a little confused. So let's take this one step at a time. So again, let's start with our painting metaphor. In the physical world, if you're standing in a museum in front of a pointillist painting, you alter the scale of that image by stepping closer to it or stepping away from it, right? You zoom in closer to the pixels or you zoom out. Now you can do the same thing on a computer monitor. You can zoom in closer or zoom out further from an image. You can do this numerous different ways. You can zoom on your monitor settings. You can zoom on a web browser. You can zoom in a graphics program. And no matter how you're zooming in on an image, you're not altering the actual file, just like you're not altering the painting in the museum. You're simply altering your relative virtual distance from it. So this is why most applications use a magnifying glass to represent the zoom function. It's just like holding a magnifying glass over a painting. You're not altering the painting, you're just altering your view of it. You can also scale or resize the actual file itself in a graphics program. Now this process of making an image larger or smaller is called interpolation. A program like Photoshop or GIMP will let you scale an image file up or down. So let's pretend you have an image which is 216 pixels high and 216 pixels wide. A typical monitor needs about 72 DPI to display a clear and crisp image. So if you have a 216 by 216 pixel image, you can show that on a monitor at about 3 inches across. But let's suppose you wanted to fill the entire background of a full 1920 by 1080 monitor. You can scale that 216 pixel image up to 1080 by 1080, but the computer will have to guess how to increase the necessary quantity of pixels. And this guesswork is known as interpolation. And it's why small images look blurry or fuzzy when you blow them up to a larger size. Now, suppose you wanted to go the other way. Suppose you had a very large photograph and you wanted to shrink it down to use on a web page. Now this always looks really good because computers are great at removing data to interpolate an image down to a smaller size. They don't have to use complex mathematical algorithms to guess and fabricate imaginary pixels. They simply remove pixels which exist. So remember that. Interpolating large images down into smaller images works great. interpolating small images up into large images works terribly. The native resolution of a computer monitor is usually 72 dpi, while the optimal resolution of a printed image is usually 300 dpi. So for example, if you want to print a 4x6 photograph, it should be about 1200 by 1800 pixels in size. That's 300 times 4 and 300 times 6. If you have an image 5 times that size, let's say 6000 by 9000 pixels, it's not going to look any better as a 4x6 because the printer is only producing 300 dpi. So all those extra pixels are useless. But if you wanted a 20 by 30 photo, that 6000 by 9000 image would be ideal. If you tried to blow up the 1200 by 1800 image into 20 by 30, it would look blurry and fuzzy because it wouldn't have enough pixels to produce a clear image.
Allow me to offer a physical example. Here are two versions of a portrait I took of my friend Katie Lohman back in 2009. One is a 2x3 and the other is an 8x10. Obviously, the 8x10 is physically larger, and therefore it has a lot more detail in the image. Now, if I zoom the 8x10 further away from you, it is still an 8x10 in size, but it will look smaller. And likewise, if I zoom the 2x3 closer to you, it will appear larger, but it's still a 2x3 image. Electronic images in the computer work the same way. We can zoom out from a large 8x10 image, and it will appear to be the same size and the same quality as a smaller 2x3 image. Whether we are in the real world or the virtual world of a computer, zooming in or zooming out doesn't change the physical size of the image. It just changes the appearance. This is very easy to grasp in the real world because we are moving in 3 dimensions. It's a little harder to understand zooming on a computer screen because we only have 2 dimensions. But the principle is identical, just like our painting behind the window. Now, let's take a look at both of those images in the computer. So right here you can see that we have our 2x3 image, and right here is our 8x10 image. And you'll notice that in the title bar of each, it says at 25%. And what that means is you are not seeing 100% of all the pixels in the image. That these two images are basically zoomed out so that they look 25% smaller than what they actually are. And you can tell the file size of the images are different by looking at the bottom right down here, the document size. Our 2x3 is only 1.54 meg, and our 8x10 is 20.6 meg, so a much larger image. So let's zoom in and out from these images just like we did with the printed image. So let's say if I zoom in on our 2x3 so that it's at 100%, now you can see it pretty much looks the same as the 8x10, right? Visually, they're pretty much the same size. But the file size obviously didn't change because all I did was zoom in closer on the image. I didn't actually alter the number of pixels in it. Now let's take a look at how many pixels are actually in each image. So our 2x3 image, if we come to image size, we can see is 600 by 900 pixels. If we switch over to the 8x10 and check that image size, it is 2400 by 3000 pixels. Now, again, the number of pixels is really the only thing that changes. The resolution of the image and the size of the image is kind of a relative thing. Now again, I know that's a little confusing. It's a little hard to understand. Don't worry. Like I said, there are professional graphic designers out there who still don't grasp this stuff. So if you don't understand it, going over a quick little tutorial like this, that's perfectly okay, because there are people who have studied this for years and they're still confused by it. But let me try to explain it as best I can. So, this checkbox right here where it says resample image, that is what allows the program to interpolate the pixel information higher or lower. So let's say, for example, that we don't want to interpolate the pixels. We don't want to add more pixels and we don't want to subtract any, okay? But we want to change the size of the print, okay? Instead of an 8x10, we want to double it. We want to make it a 16x20, okay? How do we do that without changing the number of pixels in the image? Well, the first thing we'll want to do is uncheck this box, so we're not going to interpolate. And watch what happens when I deselect that. You can see that now my pixel dimensions have been ghosted out. Now I can't change these anymore. And you'll notice that the resolution is now tied to the height and width, which it's not when this is checked. Let me show you again. See there? Not connected. And now they're connected and this is turned off. So remember, we're not going to change the number of pixels in the image, but when we print it, we want to make it double the size. So what do you think is going to happen when I change these numbers? If you said that the resolution, that the pixels per inch would be half, you were right. So if you want to make it a 16x20, but you still are working with 2400 by 3000 pixels, now you're only going to be printing 150 pixels per inch. So it's not going to look as good printed on paper. Now we can mess with this as much as we want. We could go even higher than that, right? We could go to 30 inches and then the resolution is going to drop even more. We could print it at 60 inches wide and now it's only 40 pixels per inch. So it'll print, it'll work, but it'll look really awful because the resolution will be so low, right? Do you follow this? I know it's a little bit confusing. Let's take it back up to 300 dpi. Let's put our pixels back. This is one of the most confusing things, I think, for people learning graphic design. It takes a long time to kind of wrap your head around this because of the fact that you're dealing with stuff that is all virtual and you don't have anything tangible really to touch, to hold on to look at. You can easily check the math on this and you'll start to understand it more. So let's say you've got 20 inches, right? 20 inches tall, and you're going to be printing 150 pixels for every inch. Well, 150 times 20 equals 3000. 150 times 16 equals 2400. So even though this stuff is all ghosted out, this is still all kind of interconnected, right? It's all going to match up. If you want to make the math, really simplistic, let's change the height to 30, right? Now, there you go. 30 times 100 is 3000. 24 times 100 is 2400. So you can see the pixels are never changing. No matter what we do down here, no matter what numbers we plug in, it's always going to be the width times the resolution is going to equal this number every single time. No matter what numbers we decide to plug in, that's what we're always going to get. Okay? So once you start to look at it that way, I hope that it's a little clearer and that you start to really understand it a little bit more. No matter what you change these numbers to, It's always going to exactly match the number of pixels if you decide to actually sit down and do the math. Now, let's take a look at what happens when we do interpolate things up and down. The easiest way to illustrate this is to take our little 2x3 image and try to blow it up to an 8x10 size. Now, before I do that, let's look at both images at 100%. So if we zoom in on our 8x10 to 100%, we can see here it's pretty huge, right? And at this point, you might be a little confused and saying to yourself, wait a minute, this is way bigger than 8x10, right? Like my computer monitor is obviously bigger than 10 inches wide, bigger than 8 inches wide, and this picture doesn't even fit, right? So why is it so huge? Well, remember, we're talking about an 8x10 that is being printed at 300 dpi, and a computer monitor displays images at 72 dpi. Okay? So we're actually dealing with, if we come in here again, 2,400 pixels. That's a lot, right? If we change this to 72 dpi, which is the resolution of a computer monitor, we can see it's 33 by 41 inches. So now you understand why it looks so wide, because it's basically about 33 inches wide on a monitor. Okay? Again, I know that's a little confusing, it's a little weird, but watch this video about 10 times and you'll start to understand. Okay, so we're going to take both images to 100%. All right, so we're going to take this one to 100%. We can see how good Katie looks in this shot, right? It's nice and crisp and clear. Now, if we take our 2x3, which is only 600 pixels right now, and we want to make it 2400 pixels wide, so it's the same as our 8x10. And then I click OK. Okay, now we're only at 25% on our 2x3, so it still looks pretty good. But watch what happens once we get back up to 100%. It looks terrible, right? It's not nearly as nice as this image. The image is very blurry, right? You could see the detail in her hair that's right here. That's completely gone in this image, right? So why is that? Why does this look so bad and this 8x10 looks so good? Because the 8x10 is the original image with all the pixel information, and the 2x3 image used interpolation to basically create pixels out of nothing. And when you do that, the computer always makes the stuff look a little bit blurry, looks a little bit weird, because it's not actually generating, it's not actually using real pixels. It's just inventing pixels. So allow me to show you one last example of how interpolation works in terms of making images larger and smaller. It can be a little difficult to grasp all of this when the files are separate. So let's put them together in one file. So I'm going to create a new canvas. It's going to be 20 inches wide, it's going to be 30 inches high, and it's going to have a resolution of 300 dpi. So I click OK. Here is my new canvas. And if we look at the image size, we can see it's pretty darn big, right? 6,000 by 9,000 pixels. Again, you know that 300 times 20 is going to be 6,000, and 300 times 30 is going to be 9,000. So let's move both of our images, our 2x3 and our 8x10. Let's just drag those over to our new canvas. So first we move over the 2x3. Then we move over the 8 by 10, and now we have the 2 by 3 and the 8 by 10 on the same canvas. So you'll notice here both of these images are being shown at 25%. Our larger canvas is only at 8.3%. So if I blow up this canvas so that it is also 25%, you'll notice that the images look the same, right? The size of these two images on the shared canvas look just the same as they are in the individual canvases. Because again, everything is 300 dpi, right? And everything is at 25%. So let's zoom in a little bit more on these. Let's get up to 50%, and we can see, you know, at 50%, both images look pretty good, right? So let's first show you what happens when you take a large image like the 8 by 10 and shrink it down, right? And you'll see that it's still going to look really good. So let's take our 8 by 10, let's shrink it down so it's the same size. And now if we zoom back in to 100% on both of these images, you'll see that they both look good, right? Here's our original 8 by 10, here's our 2 by 3. They still look nice and sharp and crisp and clear, and everything is very, very happy. Okay, so yeah, everything looks great if we shrink down a big image to a smaller size. So let's revert that, and now we'll do the opposite. We'll take our little 2 by 3 image and we're going to blow that up. We're going to scale it so that it is the same size as the 8 by 10, and you'll see that it won't look nearly as good. Let's take the 8 by 10 and move it over a little bit so we can kind of see both their faces. So there we go. We're pretty much at the same size for both, and even at 50%, you can start to see this image is kind of breaking up, right? It's a lot blurrier. If you look at the detail, let's say just over here in the flowers and things, you can see here it doesn't look as good. And obviously in her face, we're losing a lot, right? There's a lot of detail here in her hair that's just kind of disappearing. A lot of the fine detail in the edges of her hair are gone. If we come over here to the original image, you can see how sharp and clear her hair looks. So you cannot take a small image and blow it up, because when it interpolates all those extra pixels, it looks weird and it looks blurry and it doesn't look good. But you can always take a large image and shrink it down, and it's going to look really nice. Allow me to prove with one last example how the resolution and the height and the width of an image isn't really relevant in a computer, and that the pixels are what really matters and what really makes one image different from another. So let's take a look just at our 8 by 10, right? So this image is 8 by 10 at 300 dpi, 2400 by 3000 pixels. Let's make a duplicate of it, right? So here's an exact copy of the same image. Now I'm going to come in here and I'm going to change the size. Let's say we're going to make it 20 inches high instead, right? But we're not going to change the pixels. So now it's 16 by 20 at a resolution of 150 pixels per inch. You notice it's 20.6 meg. The pixels stay the same. So we didn't change anything, right? We just changed the virtual size of the image. Now, if we actually printed these images on paper, we would see a difference, because that is what this is controlling. The document size is controlling how big it's going to look if you print it. So this first image would be an 8 by 10 on a piece of paper, and it would be printed at 300 dpi. This second image would be 16 inches by 20 inches on a piece of paper, and it would be printed at 150 dpi. But the quantity of available pixels in each image does not change. And as we zoom in, we can see here at 100%, now we're seeing every single pixel. We can actually zoom in further than this. And as we zoom in further, we'll start to see all of the individual pixels. So we can come into 200, and you can start to see how all the little squares and all the little pixels exist in the image. As we come in further and further, you can start to notice all these individual little blocks. You can actually see every individual pixel in the image. So that's kind of cool. It's kind of neat to be able to really get in that far as you zoom in and understand that that's what this image is really comprised of, right? All of these incredibly small little dots, all these little pixels, just like the pointillist paintings. It's the same idea. This is really nothing more than a pointillist painting in a digital form. And as long as we're not changing this quantity of pixels, then the image itself really isn't changing. Now, what do you suppose would happen if we did the same thing on the smaller image, right? If we zoom into this full 1600% on our 8x10, we can see all the pinpoints of light that make up Katie's eye. If we do it on this smaller image, can you predict what we're going to see? You can kind of start to tell already, right? You can actually tell there are a lot less pixels. See, we're now at 1600% on both, and you can see the difference. The 8x10, a lot of pixels make up her eye, and on the 2x3, very few pixels make up her eye. Because again, the overall image in the 2x3 is only 600 pixels wide, right? And the overall image on this 8x10 is 2400 pixels wide.
So thank you so much for taking the time to check out my little lesson on computer graphics. These are basic design and graphic concepts I've been wanting to teach and explain for years, so it's been a lot of fun for me to finally create a little dissertation on this subject. So until next time, remember kids, the world owes you nothing until you create things of value.